In addition to digital audio processing, you can also use HiQNet London Architect to program Logic in SoundWeb London. Logic is programmed using the Logic configuration window, which is located by clicking on the Logic button. The Logic configuration window is where you place logic processing objects. You can place these objects by right-clicking, selecting New, and selecting an object off the list. For this tutorial, I'm going to use some pre-placed objects. These objects are functionally identical to the objects you get when right-clicking. The only difference being these objects have been stretched out a little bit to make more room for the names. The most basic object is a logic source. A logic source has a control panel with a single button on it. When you turn on the button, the indicator turns purple on the logic source. Turn it off, it goes back to black. There's also a logic end. A logic end has a single indicator on it. If we wire the logic source to the logic end and then turn on the logic source, you'll see the indicator turn on. Both objects have turned purple. Turn it back off, they both go back to black. That's the basic functionality of logic objects. We can take these logic objects and link them to audio objects, just like doing stereo linking of a pair of mutes or stereo linking a pair of faders. We can link the button for the logic source to a button on an audio control panel. We can use the standard linking tools in London Architect to accomplish this, or in the case of logic objects, we can grab the audio control panel object and drag it onto the logic processing object. When we see the green highlight appear, if I release the button and check the design tree, I'll see that my link has been made automatically. This mute and this logic source are now linked. I can take the master mute and link it to the logic end. And again, they will appear in the design tree. Now that I have them linked, if I turn on the left mute, the logic source turns on, the logic end is turned on because it's wired to the source, and the master mute turns on. Turn it off, they follow along. If I turn the master mute on or off manually, nothing happens. The master mute is not able to change the state of that logic end because the logic end is being held low by its wire to the logic source. We could accomplish the same end result by simply linking the left channel mute with the master mute. So this doesn't appear to be terribly useful at first. However, if we take a second logic source, we can link that one to the second channel mute, and then we can use an object called a Boolean object. There are 5 Boolean objects in London Architect. The first one is the AND object. The AND has multiple inputs and a single output. The output on the AND will only turn on when every input is currently on, right there. When 1 and 2 are both on, then the output turns on. The OR object turns on its output when input 1 or input 2 is turned on. When either input is on, the output turns on. When they're both off, it turns off. The NOT object simply turns on the output when the input is not on. The NAND object can be thought of as an AND with a NOT after it. The AND object will turn on its output when every input is on. The NAND turns off its output when every input is on. The OR turns on the output when any input is turned on. The NOR turns off the output when any input is turned on. The AND, the OR, the NAND, and the NOR are all N input objects. We can go to properties and change the number of inputs. Up to 32 inputs on each of them. A 32 input AND will only turn on the output when every input is simultaneously high. If we go back to our original DSP here, I've pre-placed the Boolean objects. Let's move this off out of the way a little bit. Let's place an AND after these two logic sources. Wire it to both logic sources. And wire it to our logic end. Now, if I mute channel 1, nothing happens to the master mute. If I mute channel 2, nothing happens to the master mute. If I mute them both, the master mute turns on. Now again, this is not the most useful circuit, but we've now built a base on which we can build additional functionality. The logic pulse is a logic object that has no control panel. It's programmed using properties. The logic pulse has an on time, which is how long it remains on, and an off time, which is how long it remains off on each cycle. Those times are specified in ticks of 100 milliseconds each. So by specifying 5, I'm saying 5 logic ticks of 100 milliseconds each. So that logic pulse will be on for 500 milliseconds, 1/2 second. Then it will be off for 500 milliseconds, 1/2 second. Then it will repeat over and over and over and over. Now if I had another logic end wired to this logic pulse, I could take that indicator and drag it to a region meter on our control panel. That produces a flashing red light on the control panel. If I tie these logic circuits together, make them function together, I can make a useful function. I can produce a function that normally we would need external devices to do. Let's grab another and a not. When do we want this light on the control panel to flash? We want it to flash when the logic pulse turns on and not the master mute. In other words, we want an on-air indicator. If everything is muted, no flashing light. Unmute it, we have an on-air indicator. We could take this logic end and drag it over to the design tree, link it to a control port, and drive an LED in the real world, or trigger some external logic. The next object we should look at after the logic source and logic pulse is the calendar object. The calendar object, like the logic pulse, has no control panel. It's programmed using properties. If we go to properties, click on the button, double-click on a line, we can place a trigger for this calendar object. If I create a trigger at 5:05 p.m., starting today, turn the trigger on and recur every 1 day. Double-click, create another trigger at 7:55 a.m. to turn the trigger off and recur every 1 day. I've now programmed this calendar object to turn itself on at 5:05 p.m. and off at 7:55 a.m. every day. Now if I come back to my original circuit, let's peel this back, and we'll drop an OR into this circuit. Now, when is our master mute going to engage? Our master mute will turn on when logic source 1 and 2 are both turned on. Those are linked to our mutes. So when mute 1 and mute 2 are both turned on, the logic end for master mute will turn on, or the master mute will turn on when the calendar tells it to turn on. We've now programmed this system to mute itself automatically at 5:05 p.m. every day and unmute at 7:55 a.m. every day. This is a real-world example that was requested by a school for one of their projects. Originally, the installer thought they were going to have to install a control system from a third-party controller just to do this simple timing, the simple scheduling logic, to make sure the system in the school was muted after hours. After looking at logic, they realized they didn't need to. It could all be done in SoundWeb London using logic processing. They even went one step further, because in the calendar object, we can have overlapping triggers. In other words, I can double-click, program a trigger for 7:55 and 1 second a.m., starting on Saturday morning, to turn the master mute on and recur every 7 days. Now, on Saturday mornings at 7:55:01, the system is going to remute itself. It'll unmute at 7:55 and mute again at 7:55:01. Now, this is going to overlap with the 5:05 p.m. trigger, because at 5:05 p.m., the trigger will be told to turn on, but it's already going to be on from the morning trigger. That's no big deal. It won't bother anything. It'll work just fine. The calendar object does not toggle when the trigger time happens. Instead, it sets itself on or off based on the way you programmed it. I can do the same thing for 7:55:01 a.m. starting on Sunday. And now this audio system will only work Monday through Friday, 8 to 5. Total time required to program this, less than 30 minutes. And additional equipment needed? None. It's all self-contained within SoundWeb London. Now those are really the only 3 objects that can start a logic chain: the logic source, the logic pulse, and the calendar. However, the logic source actually comes in 3 flavors, and it's disguised as 2 more objects: the logic comparator and the logic value objects. They're really logic sources. The logic source has a button on the control panel, and it can be linked to any button on any audio control panel. The logic comparator does not have a button on its control panel, and it's designed to be linked to a fader or a rotary. If I grab this fader, drag it over until I get the green outline, drop it in place, it's now linked. On the control panel, I have a raw value. That's the hexadecimal value of this fader's current position. If I move it, we'll see that change. Down below in the value field is the value that we're going to compare against. It's a logic comparator. We're going to compare against this value. If we look in properties for this object, the compare operator is currently set to equal. Let's change that to greater than or equal to. Now the compare is if the raw value is greater than or equal to the compare value, turn on this logic comparator, which means if my fader is equal to or greater than 0, turn on the comparator. If it's below, turn it off. If I want to compare a different value, let's say -8.6, I enter that value and then hit the copy button. That will place that value into the compare value field. Now, I'm turning it on when I'm at or above -8.6. If I'm below, it turns off. The logic value does much the same thing, but for source selectors. Has no control panel at all. If I drag my source select over, drop it on, If I go to the first source, my first output. Second source, second output. Logic value, of course, is an N input device. It can have multiple outputs, and those outputs can identify the linked state variable as a binary set or straight shift down set. What that means is if I had a 3 output logic value set for shift down, that could indicate up to 3 values on a source selector. If I change that to binary, 3 outputs could indicate up to 8 different states because it treats those 3 outputs as a binary set. So those 3 are really the exact same thing in different forms. On the output side, on the finishing side of a logic chain, we've already looked at the logic end. We also have preset triggers and preset tables. With a preset trigger, I can go to Properties, click on the drop-down, and select any parameter preset or venue preset to be triggered when that preset trigger goes high. So when logic drives that high, it will trigger preset unity. When logic drives it low, it does nothing unless I program another preset. The preset table also triggers presets, but instead of treating its inputs as individual discrete inputs, they're treated as a binary set. So when I click under Properties, I see every possible combination for those inputs, up to 12 inputs, and I can assign a preset to each of those combinations or to any of those combinations that I want to use. The serial trigger table is very much like a preset trigger and a preset table combined. If I set it for 3 inputs, click on the button, I see that for each input I have an on and an off. But instead of assigning presets, I'm going to enter serial strings to be transmitted out the serial port on the back of the blue box. So using the serial trigger table, I can remotely control external switches, lighting systems, projectors, displays, anything that can receive an RS-232 serial signal from that device. If I switch this object to table mode instead of list, now it treats those 3 inputs as a binary set. Instead of having 6 possible strings I can send, I now have 8 possible strings. The serial trigger table is limited to only 12 possible inputs, so you have only 4,096 possible serial strings that you can trigger for each serial trigger table.